All right, so we saw that you could represent the motion of a simple harmonic oscillator on a horizontal position graph, and it looked kind of cool. It looked something like this. And the amplitude of that motion, the maximum displacement from equilibrium on this graph, was just represented by the maximum displacement from equilibrium. It looked like this. And the period, which was the time it took for this entire process to reset, capital T is the period, this is the time it takes to reset, was the time it takes to reset, which would be from peak to peak, or from trough to trough, or from any point to any analogous point on that cycle. This was the period T. And so with a graph that's a sine or a cosine, you could represent any motion you want. So if you had some oscillator that had a larger amplitude, you could imagine just stretching this thing vertically. The period would stay the same, but you could stretch out the amplitude. Or if you had something with a larger period, you could imagine stretching it out horizontally and leaving the amplitude the same, or stretch it both ways to represent any oscillator you want, which is kind of cool. However, a lot of times you also need the equation. In other words, you might want to know what equation would describe this graph right here. What equation would represent this graph here? First of all, what do I even mean by like the equation for this graph? What I mean is that this graph's representing the horizontal position x, which is how far the mass has been displaced this way from equilibrium, as a function of time. So we want a function that will be, all right, what is the value of the position of this mass as a function of time? So what would this equation be? It's going to be a function. In other words, you're going to feed this function anytime you want, and the function's going to give you, it's going to spit out a value for the position, and that should represent whatever position this graph is representing where the mass is at, because the graph should agree with what this function is going to tell us, and this function would tell us where the mass is at any given moment. So what would this look like? Now we saw, like, this is a sine or a cosine, right? So this is either a sine or a cosine. That's the first choice. Do we want to pick sine or cosine? And what I always do is I just look at the beginning and I say, all right, at t equals 0, this one's starting at a maximum. So I want to use cosine because cosine starts at a maximum. And by starting at a maximum, I mean, think about it. For cosine of 0, if you remember your trig functions, cosine of 0 is equal to 1. And so because this is as big as cosine ever gets, sine and cosine can only ever get as big as 1. This thing is starting at a maximum. So cosine starts at a maximum at t equals 0. This function here starts at a maximum at t equals 0. I'm going to want to use cosine, but I'm going to have to add a few elements in here. Just cosine alone isn't going to do it for me because cosine only gets as big as 1. This thing has to get as big as a. Whatever a is, this thing has to get that big. So in other words, my simple harmonic oscillators aren't always going to have an amplitude of 1. So I need some variable in here that will represent what the amplitude is for that given simple harmonic oscillator. Let me make this less abstract. Let me just say, let's say we happen to pull this thing back 20 centimeters or 0.2 meters. So let's say our amplitude for a particular simple harmonic oscillator happened to be 0.2 meters. That would mean that this here, I could represent this here with 0.2 meters. This doesn't even make it to 1. So if I just left this as cosine, that would say this thing's going to get as big as 1 at some point in time, and that's a lie. This thing only gets as big as 0.2. So it's easy though. You might realize, if you're clever, we'll just multiply the front of this thing by the amplitude. Whatever the amplitude is, multiply it, because then 1 times amplitude means that this x only gets as big as the amplitude, which is exactly what I want. I want this thing to be as big as whatever the amplitude is of the motion. And then there's one more piece. You might be like, all right, we're done. I'm just going to stick cosine of t in here. That's not going to work. We do want this to be a function of time, right? We want to be able to plug in a time and have this function spit out what is the value of the position of the graph. And that would represent where is it. So is it at 0.2? Is it at 0.1? Is it at 0.045 or something like that? That's what this function is supposed to do. But just plugging in t here, just having t alone, isn't going to be good, because that would mean, look, at cosine of 0, we know cosine's 1. When does cosine get back to 1? That's going to be when the inside, the argument in here is 2 pi. So we're going to be using radians. You could use degrees if you wanted to, but most physicists and professors and teachers are going to be using radians for this case. So cosine of 2 pi would again be 1, because that's when, if you remember your unit circle, that's when this function for cosine has gone around one whole time and it gets back where it started, right? So if something rotates through an angle of 2 pi, you've reset the whole thing and that process has reset. But that would mean this function resets every 2 pi seconds, right? Because at t equals 0, the function was 1. And then at t equals 2 pi, the function's 1 again. That would mean the period for cosine of t is 2 pi, but our period isn't necessarily 2 pi, right? Unless you've got a really special case, the period is whatever the period is. Let's say our period happened to be like 6 seconds for this particular case. So if this was 6 seconds, we would not want a function that resets after 2 pi seconds. We need a function that resets after, for this case, 6 seconds. So how do we do that? Well, we have to not just have t in here. We saw that if we just have t, the period is always 2 pi because that's when cosine of t resets. How would we do this? Well, we're going to be clever. And if you're really clever, you realize, all right, I'm just going to add a little variable in here. I'm just going to add a little variable, boom, omega, and then multiply that by t. And then I can tune this omega however I want, right? If I can make omega big or small, I can make the period of this function whatever I want. And if you're curious, you might be like, wait a minute, omega, we've used that before. And you'd be right, omega we have used before. That was the angular velocity. And remember, angular velocity was delta theta over delta t. The amount of change in angle over the amount of change in time, which you might think isn't relevant here, because this mass is just going back and forth. This mass isn't actually rotating in a circle. However, you can represent repeating processes, cyclic processes, processes that go through a cycle on a unit circle. So in other words, let's say you start right here, right? So at t equals 0, you start, we pulled this mass back and then we let go. So we start right there. That would be right here on this unit circle. And then it flies through the equilibrium point. That would be through a quarter of a cycle. That means it would have made it to right here. And then it makes its way over to this edge, fully compresses this thing. That would be over to here. That would be through half a cycle. And that would come back through, let me find another dark color. It would come back through the equilibrium point, and that would be down here. And then we get back to the initial point, and that would be one whole cycle. So you can see how we can represent cyclic processes on a unit circle, and that's how this makes sense. That might seem abstract, but it's really useful because watch what we could do. Naively, you might think, all right, how would we even define this? Well, one cycle on a unit circle is 2 pi radians, right? If we're using radians, then one cycle would be 2 pi because 2 pi is once around the circle. And how long does that take? Well, I know for a simple harmonic oscillator, we've defined the period to be the time it takes for one whole cycle. So we'd have 2 pi over the period. And this is what you would plug in down here. So it turns out this does work. So even naively, just using our ideas of angular velocity, plugging in 2 pi over the period will give us a function that resets exactly when we want it to. And you might not be convinced. And if that doesn't make sense, I don't blame you. I might be confused too. So let me show you what I mean. In other words, if we take this function, instead of writing omega, we can just do this. We can just be like, all right, forget this. Taking this, omega is the angular velocity. Sometimes it's called the angular frequency in this case. So people use different terminologies. You'll hear it as angular velocity or angular frequency. If you take this angular velocity or angular frequency, we just smack that right in here. So we just put that in for omega and then multiply by t. Watch what happens. This is beautiful. So if we take this, now it's going to work. So we multiply by t. T is our variable. So little t is our variable. 2 pi is a constant. The period capital T is also a constant. It'll be different for different harmonic oscillators, but for a given harmonic oscillator, capital T, the period, is a constant. So watch what happens now. At t equals 0, this whole inside becomes 0. So let's say I plug in t equals 0. We get to plug in little t, whatever we want. That is our variable. So if I plug in little t equals 0, cosine of 0 gives me 1. But now what happens? If I plug in t equals, all right, after one whole process, right, after one whole cycle, it's gone through one whole period. So if I plug in little t as capital T, the period, look what happens. This capital T cancels with that capital T, and you just get 2 pi in here, and the cosine of 2 pi is also 1. That means this thing goes through a cycle every capital T, period. That's what we wanted. We didn't want something that always had to have 2 pi as the period. Now we've got a function that we can plug in whatever our period is down here. That way, whenever this little t makes it to the period, capital T, this whole argument in here becomes 2 pi, and the cosine resets itself, and you get a graph or a function that will give you a graph that resets every period, which is exactly what we wanted. So in other words, to make this less abstract, let's take this thing here. For this particular function here, for this particular choice of amplitude and period, we could say that the graph that's representing this. So the function that would represent this here, instead of amplitude, we'd plug in 0.2. So 0.2, let me try to fit it in here. 0.2, I'm going to put the units down here, meters, times cosine. Remember, we wanted cosine because it starts at a maximum, and this graph started at a maximum. If it started down here and went up, I'd use sine, because sine starts at 0. But this one started at a maximum. And I have 2 pi over the period. I can't just leave that as period t. That's a little bit vague. I'd put in my actual period. And we said that the actual period for this mass on a spring was 6 seconds. And then little t, a lot of times people get confused. They're like, all right, what do I plug in for little t? You don't, typically. Like if you just want the function for the position as a function of time, you leave little t as the variable. That's the variable that you have sitting here, right? If I wanted to know what is the value of the position of this mass at 9 seconds, I would plug in 9 seconds. I would calculate this function with the 9 seconds in there. That would be the position at 9 seconds. Or if I wanted the position at 12.25 seconds, I'd plug in 12.25 seconds for our little t time, calculate this function, plug it into the calculator, in other words, and that would give me the position at 12.25 seconds. That's what this function can do for you. That's how it can represent the motion of a simple harmonic oscillator. And now you might be like, dude, that took a long time. Do they all take that long? No, once you get good at this, it's really easy. Watch, let me get rid of all that. Let's say you got this problem on a test or a quiz or whatever on homework, and it was like, hey, make an equation that describes this simple harmonic oscillator. It's easy. First thing you do I want to use sine or cosine? So you might be like, oh, crud. It doesn't start at a maximum. And it doesn't even start at 0. Sine would start there. It starts down here, but that's okay. It starts at a minimum. So we're still going to use cosine. So we're going to say that x as a function of time is going to be, what's the amplitude? The amplitude here is 3 meters. So 3 meters is our amplitude because that's the maximum displacement from equilibrium. So I'm going to have 3 meters out front. And then I'm going to do cosine because it starts at an extreme value, either a maximum or a minimum value, cosine of, and then I need 2 pi over the period. What is my period? I look at my graph and I ask, how long does it take to reset? So it started down here to minimum. When does it get back to a minimum? That took 4 seconds. So 4 seconds would be the period. So it'd be 2 pi over 4 seconds. And then little t, what do I plug in for little t? I don't. This is the variable that sits there and waits for me to plug in whatever I want. So that's my variable little t that x is a function of. But I'm not done. This would be a graph that starts up here and goes down like that. This graph starts down here, but that's easy. Just multiply by a negative sign out front, and you've turned your cosine into negative cosine, and negative cosine starts down here. So note, our amplitude is still 3. If the question asked, what is the amplitude? The amplitude is the magnitude of the displacement, maximum displacement. So that's still positive 3 meters, even though it started down here. But you could just include an extra negative out front that essentially goes along with the cosine. That would give you negative cosine. And there you have it. That would be your function. So keep in mind, it's good to remember, if you start up here, you're going to want to use cosine. If you start down here, you're going to want to use negative cosine. If you start right here, you're going to want to use sine. If you start here and go up, that's going to be sine. And if you start here and go down, that's going to be negative sine. That's what those functions look like. So recapping, you could use this equation to represent the motion of a simple harmonic oscillator, which is always going to be plus or minus the amplitude times either sine or cosine of 2 pi over the period times the time. This 2 pi over the period is representing the angular frequency or angular velocity, and you would choose positive cosine if you started at a max, negative cosine if you started at a min, positive sine if you start at 0 or equilibrium and go up, negative sine if you start at equilibrium and go down.